Welcome to this lecture series in linear algebra. In this lecture, we'll show a very nice property of upper triangulable operators, which says that if T is an upper triangular operator and suppose we find a matrix representation of it which is upper triangular, then the eigenvalues of T are precisely the entries on the diagonal of this matrix. So we will properly write this down, but let us recall all the facts that we need to prove it. So first fact is about minimal polynomials of an endomorphism, and so let me just read it out. So fix an endomorphism on a vector space V over a base field F, which we suppress. Suppose W is a T invariant subspace. Then we get an endomorphism on W and an endomorphism on the quotient, which behaves like this. We have seen this multiple times. So then the minimal polynomial of T divides the minimal polynomial of the restriction times the minimal polynomial of the one on the quotient, and each of these, meaning the minimal polynomial of this guy and the minimal polynomial of that guy, divide the minimal polynomial of T. So this is not a product. Here we have a product, but this is not a product. Okay. We have seen that roots of the minimal polynomial of any endomorphism are precisely the eigenvalues of that endomorphism. Okay. And the minimal polynomial of an endomorphism splits over the base field if and only if the endomorphism is upper triangulable. So we will use all these facts. Here are some problems for practice. And now let us get to the main theorem. So the formal statement is this: fix an endomorphism on a vector space V and F is the base field which we suppress. Suppose there is a basis B such that the matrix of T with respect to B is upper triangular, so this is an upper triangulable endomorphism. Then the eigenvalues of T are precisely the entries on the diagonal of this matrix. No matter what matrix, no matter what basis you pick such that this is upper triangular, the entries on the diagonal are precisely the eigenvalues of T. Okay. So let's prove it. So suppose not. We go by contradiction. And we have seen this kind of approach many times before. So let V be a vector space of smallest possible dimension such that there is an endomorphism on it and a basis of it such that, or with the property that the matrix of T with respect to this basis is upper triangular, but the set of the eigenvalues of T is different from the set of all the entries on the diagonal of this matrix. So it's a long statement, but it is just an enunciation of this fact. Okay, and I want you to check that the dimension of V is necessarily greater than or equal to 2. So what we have done is we have picked a vector space of smallest possible dimension where one can find a counterexample to this theorem. And easily one can see is that it cannot be a one-dimensional vector space, because there you cannot find a counterexample you can easily show. So this I leave you to check. All right. So say the basis is V1 up to Vn, and the matrix of T with respect to B is something like this. So above the diagonal there is something, below the diagonal everything is 0. On the diagonal the entries we denote by lambda 1 up to lambda n. Okay. So note that Tv1 is therefore lambda 1 v1, just immediate by this matrix representation. and we define W as span of V1. T bar is an endomorphism on the quotient. So yeah, so this is a T invariant subspace simply because of this equation. And as always, T bar is behaving like this. All right. So what I want you to check, which we have done in previous videos, is that B bar defined as V2 plus W dot 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 Vn plus W is a basis of V mod W, and the matrix representation of T bar with respect to B bar is this. So what do we mean by that? We just mean that you slash off the first row and slash off the first column from this matrix, and what remains is this. So this you can easily check. Basically, all we need is that the diagonal entries are all these things, meaning all of these things except lambda 1. So that I leave you to check. And now, therefore, by the minimality of the dimension of V, the eigenvalues of T bar are precisely the entries on the diagonal of this matrix. So let me explain that. We see that B bar is a basis such that matrix of T bar with respect to B bar is an upper triangular matrix. And since V was a vector space of smallest possible dimension where one could find a counterexample to this theorem, the eigenvalues of T bar must precisely be these numbers. And that's what we have written here. Okay, and now let us introduce some notation. So let Mx be the minimal polynomial of T. Sx be the minimal polynomial of the restriction of T to W, and Qx be the minimal polynomial of T bar. So first of all, we know that Mx splits over the base field. Why? Because T is an upper triangulable operator, and this is what we recalled. So that splits. Other thing I want you to check is that Sx is nothing but x minus lambda 1. This is a trivial exercise. And Qx splits over F. Again, because T bar is an upper triangulable operator. So these things we have. And here is the thing. So here is the statement I want to make. The set, maybe I'll use a different color. So the set, sorry, this is a 2, is precisely the set of all the irreducible factors of Qx. Alright, so this is what I want to justify. I will say this in words. So first of all, we know that lambda 2 up to lambda n are eigenvalues of T bar. Hence, each such thing is a root, so lambda 2 up to lambda n are eigenvalues of T bar, and hence each of these guys are roots of Qx, because roots of the minimal polynomial are precisely the eigenvalues. And since these are roots of Qx, each of these is a factor of Qx. So what we have seen just now is that this set is contained in the set of all the irreducible factors of Qx. That much is clear. For the converse direction, first of all note that since Qx splits, every irreducible factor of Qx is of degree 1. That's immediate by splitting of Qx. Okay, and if you have a degree 1 factor, it corresponds to a root of Qx and hence to an eigenvalue. So therefore, every irreducible factor has to look like one of these. because if there were some other irreducible factor, let's call it x minus a, sorry about that, x minus a, then a would be an eigenvalue, but then a would have to be equal to one of these people. So that's it. So we have justified that statement. And now, by what we recalled earlier, Sx and Qx divide Mx, and we also know that Mx divides Sx times Qx. Okay, so what does the first one tell us? The first one tells us that x minus lambda 1 and each of these people are irreducible factors of mx. X minus lambda 1 is equal to Sx, so that is clear that x minus lambda 1 divides mx. And since x minus lambda 2 divides this and this divides that, we have x minus lambda 2 divides that, and similarly dot dot dot. So the first one concludes to us that all of these divide mx, and hence each of these are roots of mx, and hence lambda 1 up to lambda n are definitely eigenvalues of the endomorphism T. So we have shown that the diagonal entries of this matrix are definitely eigenvalues of T, and now we need to do the other direction. So suppose there is some other eigenvalue lambda of T, and hence x minus lambda is a factor of this guy, and hence and so we want to show that lambda is one of these lambda i's, lambda 1 up to lambda n basically. So fix an eigenvalue lambda of mx, fix an eigenvalue lambda of T, hence x minus lambda is a factor of mx, hence x minus lambda divides this guy, hence x minus lambda either divides this guy or that guy. If it divides this guy, then x minus lambda is equal to x minus lambda 1, and hence lambda is equal to lambda 1. If x minus lambda divides this guy, then it has to divide one of the irreducible factors of this guy, right? And hence it has to divide one of these guys. And hence it has to be equal to some x minus lambda I, which again forces that lambda is equal to lambda I for some I. So dot dot dot, I have said it in words and you can fill it. And this completes the proof, because now we have shown that, so finally, I mean, this is exactly what we wanted to say, that the eigenvalues of T are precisely the numbers lambda 1 up to lambda n. And that's what we just argued by these two statements. So that's it. And as usual, like, comment, share, subscribe. And I'll see you next time.